Started. We have today and Thursday for the last of the new content. The good news is the new content really doesn't have any new skills. It's application of what we've already been doing. And we get exact answers, in my opinion, a little easier as long as you're comfortable with doing derivatives in reverse, right? Getting the antiderivative. So we'll be doing that in today's, and then we'll see that what we do today is a special case of what we do on Thursday. So Thursday just expands it a little bit. Nothing overly new again, just a slightly general application of what we're doing today. Next week we'll have Tuesday to do a review for the third exam. And remember, the third exam is a good opportunity to do really well because it's less material. It's really antiderivative, applications, Riemann sums, all these things we've been doing. But it's fewer sections, and yet it counts the same as test exam 1 and 2. So it's that place. And then remember, your lowest exam can be replaced, that score can be replaced with what you do on the final, as long as the final's higher. We would certainly hope so. Okay, and then also I will look overall and see, regardless of points, have you shown enough progress that you've got scores that you've demonstrated enough understanding that you can earn a passing grade. Again, if sometimes you got to take a class again if it's going to be needed, but we also don't want to hold someone's back who's maybe, a little bit. Okay, so we'll do all of that. So keep up the progress. I don't have a review for the third exam. I don't think we had one in the spring, so but this course has been copied over. So I will get those in there. There's actually, review for exam 3. Maybe we did. But I will get the updated one. Again, they make slight changes, but we'll make sure that for exam 3, everything's there by the weekend time, so you can start doing the review over the weekend. Come with any questions on Tuesday. We'll work through some things and get ready for that exam. All right, so today is 13.4, called the definite integral, which we sort of started on last Thursday with Riemann sums. We were looking at one way of getting what we call the integration is to get the area underneath the derivative curve using geometry. And that's what the Riemann sums were, little rectangles that we all add up. So it was really just a geometric approach. Today we're going to go with an analytic approach of using the antiderivative. So we take the derivative, we get back to the original function. And what is the original function? It's an amount of stuff. It's not a rate, it's an amount. And so we can actually directly calculate how much stuff do we have. What is the total cost for either from 0 to whatever, or for a smaller section. So that's what we pick up today. And what we're going to see is, remember when we took that antiderivative, when we were working with indefinite integrals, we always had that plus c, plus a constant, plus k sometimes they put. But that was because when you take a derivative, the constant, a number, disappears because its derivative is 0, right? It's a horizontal line, has a slope of 0. So it disappears. So if it was 1,000,000, it's gone. If it was 2, it's gone. But when you integrate, you don't know what it was unless you have additional information, right? What we're going to see today is that's not going to matter. And the PowerPoint from the text will highlight that, because basically it'll cancel out. It doesn't matter what it is. It'll cancel out in the way we do the calculation. But what we're going to be able to do now is our answers will actually not be a function. We might get a function as an intermediate step, but our answer will be an amount of stuff, right? Not a rate, but an amount of stuff. Okay, so I thought I would just start with a problem example. I'm going to work through it with sort of the new notation and how we do it, and hopefully you'll see it's not overly new. It's something that's understandable, and then we go through all this, maybe 4 or 5 slides where the text introduced what we did. Okay, but I think sometimes it's easier, instead of talking about it, just do it, and it makes sense because you see it. You know, or if it doesn't make sense, then we'll pick it up afterwards. So that's how we'll do it. So we're going to do this example problem, and let's go with blue. So they tell us we have a marginal cost. What is marginal? When we see that word marginal, what do we first think of? Or what should we in the calculus class? Derivative. We have a derivative. It's a rate. It's how much costs for that next one. So it's a rate of change for that next cost. So it is a derivative. So we see the word marginal. That means we've got a derivative. So the marginal cost of producing baseball caps at a production level of X caps. So X is going to be the number of baseball caps we produce. They give us this function, and there's another indication in here that this is a derivative. Remember this word per. Look for the word per. That's going to remind you that is a rate. That is a derivative. Okay? And remember, a lot of what we do in this class, you've got to be using the right function. Sometimes we want the total value function that came before the derivative. Sometimes we want the rate function that is the derivative. And that's one of the hardest things, or it is a difficult thing. I don't know if it's the hardest, but it's a difficult thing to pick up. I struggled with it as a student, and sometimes I fall into the same traps. I'm using the wrong function for what they're asking. They want an amount, and I'm using the derivative. No, that's not going to work. They want a rate, and I'm using the original function. It's not going to work. Okay, so that's part of it. We have to remind ourselves what we're dealing with. So this is a derivative function. Then they ask us to find, notice, the total change. They don't want a rate. They want a total. So that's telling us we need that we need to get the antiderivative, or we need to get the area under this curve. So we're going to see there's 2 methods. We're going to use both of them. Okay. One involves more technology. So the nice thing is today we pick up a use of the calculator. TI-84 is good, or Casio's work. They'll be able to do this. That will do the integration through technology, give us the answer. We'll also look how to do it sort of by analytic, by calculus stuff, and so we'll be able to check our answers, which is nice. So total change of cost production is increased from 100 to 200 caps. So we want to know how much does the second 100 caps cost us? What was the total cost going from 100 to 200? And notice when we're producing things, sometimes that first 100 might have been more expensive because there's startup costs and stuff. Maybe the second is cheaper, or maybe it's more expensive, whatever. But we just want to know how much that extra 100. The client says, oh, we ordered 100. How much would it cost us to get another 100? Oh, let me see. We got it. Okay, so that's what we're doing today. So what this means is we're given a derivative. We're going to want to integrate it to get its antiderivative, because that will give us the total function. So we put that in here, 4 minus 0.001 x dx, and that dx is an indication that this is a derivative as well. Okay, so those are those. This we did in 12.1, find the antiderivative. What we're going to add today is, to make this a definite integral, is we're going to add these boundaries. We want to go from 100 to 200. And we put those numbers right there on that integration symbol. Bottom, the lower limit, and the upper limit. Okay, we'll see, we'll use this. So now all we do is step back into 12.1, integrate it, and then we'll show you the newer step after that. So when we integrate this, and notice we're going to integrate term by term. There's 2 terms. There's the term 4, and there's the term 0.001x. What do we get when we integrate 4? 4x. So whenever you got a constant, a number, when you're integrating, it becomes that number times x, right? Because it's really like 4x to the 0. if we wanted to. So I'll put that in there. It's really x to the 0, which is 1. Add 1 to that exponent, you've got x to the 1. Okay, so yes, we get 4x to the first power. That's all that. So that's integrated. We integrate the next term, which is 0.001x to the first power. We add 1 to that exponent, right? So we're going to get 2. We'll get minus 0.001x squared, and then we divide by that new exponent. So far, so good? So that's the stuff from 12.1. In 12.1, we would put plus a constant, but I'm going to show you it's not needed. We'll talk about it a little bit later. Basically, it would cancel out with what we're going to do in the next step. But so far, we do this. And then now that we're doing definite integrals, what we do is we carry our boundaries forward with a little straight line down here, and we say we're going to go from 100 to 200. Okay. So now let's talk about what is this new function that we have. This is not a rate function. This is a total function. If we plug in 200 to this function, what is it going to give us? It's going to give us the cost of 200 baseball caps. If we plug in 100 to this function, what is that going to give us? The cost for producing 100 baseball caps, and the first 100, right? So if we take the cost of producing 200 total caps, and then we subtract off the cost of the first 100, what do we get? We get the cost from 100 to 200. And that's exactly what we're going to do. Okay? So the process is we take our function, 4x minus this. You could simplify this to 0.0005, take 2 into it, or we could just leave it. Again, the nice thing is we are going to have a numerical answer, so we don't care so much about the pretty algebra along the way. Unless you do. If you care, that's okay. You can simplify things, but we can also just leave it as numbers, plug it in the calculator, and at the end we've got the same number, right? So I'm going to leave it there just for simplicity's sake. We're going to plug in 200 first. So I'm going to have 4 times 200 minus 0.001 200 squared, all divided by 2. And notice I could just calculate that, so no need to do it. And then so that's going to give us the cost of 200 baseball caps. Total 0 to 200 really is what it's going to give us. And then we're going to subtract off, and I'll put a big old bracket, parentheses, just because this subtraction has to apply. I've got two terms, it has to distribute to both. So that's one of the biggest errors I've seen made. That's one of the biggest errors I make, is I put that negative on the first one, but I don't distribute it, and so I get a wrong answer. So we're going to put in 4 times 100 minus 0.001 times 100 squared all over 2. And actually, we don't have to worry too much about distribution. We just calculate these two numbers separately and then just subtract them. So after this, we've got it set up. It's all arithmetic. It's all arithmetic. Okay? Addition, subtraction, multiplication, division. There's no variables left, right? So what's 4 times, let's go ahead and do that. 4 times 200 should be what, about 800? Let's see. Uh-oh. Come on. 4 times 200 minus 0.001 times 200 squared divided by 2. I come up with that this first part here, just plugging it into my calculator, I have 780. And again, one of the things you're going to want to watch out for is your order of operations, and because you just plug it in your calculator, you put an answer, and usually you don't write down what you put in your calculator, so we have no way of noticing what's there, but sometimes we get our parentheses off, so double check it, and that's what's nice. We're going to use the technology to double check our answer as well. And then I'm going to subtract, that's this negative here, I'm going to get this number, Again, I'm just going to plug this whole thing. 4 times 100 minus 0.001, 100 squared, and that is divided by 2. And I get 395. And now I take 780 minus 395. Plug it in the calculator. I get 385. What are the units on my answer? What is 385 what? Very good. It's a total cost. So that's a key part. It's not hats. It's not dollars per cap. It's not a rate. It is an amount, and it is dollars, because this is a cost function. So always bring yourself to do that, because otherwise, 385, sometimes our brain's thinking, oh, X is, X is caps. Yeah, so maybe we thought we solved for X. No, we didn't. We solved for the cost. We plugged in X. 200 was X. 100 was X. This is dollars. Okay. And in the math class, we're working on the technique and getting there. But in the real world, you got to know what you got, right? You don't want to tell your boss, oh, we got to make 385 caps. He goes, well, that doesn't make sense. No, it's going to cost us 385 to make that second 100, right? To make 200, it costs 780. So notice the first 100 cost us 395. It's all right there. Second, we saved about $10 on that second 100. So maybe the more we make, we save some money. That seems to be what's happening. So that's the first method. And again, we'll go through the slides, and we'll see the same stuff worked out a little more painstakingly and giving us the notation and everything. But I want to also show you, while we're at it, the second method, which involves, let's see, I don't want to erase this yet, involves using the graphing calculator. TI-84 has a great feature in here. What we do with this is we're going to put in the derivative function, right? We don't even have to integrate. We put in the derivative function. This is why it's such a great way to check. If we made an error in our integration, we'll still check it. We'll catch it, because what we're putting in here is what they gave us. They gave us 4 minus 0.001 x. I have to go here. Oh, shoot. Let me try it this way. 4 minus 0.00. Oops. See, you still make mistakes. I do anyway. 1 x raised to the... No, it's not raised. We didn't integrate. It's just x, right? Let's see if I can... There we go. So that's what they gave us from the problem. We put it in here. We know we're going to go from 100 to 200, and that's the number of caps. That's x. So what we're going to do is that helps us set up our window so we can see it in the graph. I'm going to have our graph go from our x minimum. I do -1 so I can see 0, and then let's go to 200. Let's go to 250. Again, since I know I'm going all the way out to 200, let's go a little bit bigger. What about the y value? Well, remember, this is a rate, cost per cap. Look at that function. It's 4 minus 0.001x. So whatever x is, we're subtracting off of 4. 4 is kind of like going to be the biggest value. And if you don't get this right, you just graph it. And if it's zoomed out too much, you zoom back in. But I try to get it right if I can. So -3 to maybe 7. That's good. We'll be able to see the whole graph. And I'm just going to hit graph. And yeah, because of the way I've got it set up, it looks that way. So let me do one little trick. There we go, that, and then I'm going to change my window -10 to 250. I think that's easy. So I went from a standard window. That still gives us a pretty good view. And so now what we can do, remember, this is a rate curve, right? This is the rate of, so that's a marginal, how much to produce each additional cap. So it's just as it goes down, it's a little less than $4 for each additional cap is what's happening. But what we can do is the area under the rate curve is a total. It's also going to give us a total value. So we go second, calc, and calc is the shifted trace button. So I hit trace, second trace. And what I'm going to do is number 7, which is integration. So the calculator is going to do the integration. So number 7. And when we do this, the calculator is going to first ask us what is our lower limit. That's the 100. That's at the bottom, right? Enter. Now it asks for the upper limit, 200. It shows us the area under the curve that it's getting, and it gives us the answer of 385. Hey, that's what we got with the other method. It looks like we did everything correctly. See, we're going to be able to do this. On the homework, you're going to be able to use either method. Again, you could use this because all you have to do is enter 385 and know that that's $385. What I'm going to encourage you to do is use both each time. And I leave it up to you whether you want to do the graphing part first to get the right answer. Then sometimes you know what your target is, and you can catch errors along the way possibly. Sometimes you want maybe practice with a, let me try integrating and see what I do and check it second. So it's up to you. Do what you need. But get good at both of them so you have two methods. And if one isn't working as well, at least get one that works well for you, So technology will work. Okay? And basically in one slide, any questions on that? So that was like the Riemann sums one, right? But except that we got the exact one because it's built, the technology is built into the calculator. So in one slide, this is basically the lesson. What we're going to do now is walk through and go through the definitions that it all works from the text, and we'll look at a few more examples. But this is all we're doing. Okay, so notice it's nothing overly new. It's going back to 12.1, but adding this little thing that we could have probably skipped 12.2 and 12.3 on. We didn't really need Riemann sums because, like I told you, we weren't really going to use them because we've got something more accurate. Riemann sums were just to kind of give us some basis that what we're doing works. Area under the curve does give us the same answers. Okay, so here's the textbook. It just gives the same problem. They tell us, oh, we need the cost function, so we need the antiderivative. Okay, that's what I said, but it's all in writing here. We need to look for the antiderivative. Okay, so they recognize that the function we're given is a derivative, and they set up the integration just like we did. They integrated, and they went ahead and put the plus a constant, but you're going to see we're not going to need it. So I said, just trust me, we won't need it, so let's not put it. But they put this constant here, and then they simplify. Again, we didn't. We just let the 0.001 x squared divided by 2, but you can simplify it as you go. And they recognize that while we don't know the constant k, we could plug in 100 caps, and they did that, and so they got 395 plus a constant. Notice we just got 395 when we did it because we didn't put that constant because I was telling you we wouldn't need it, and next slide we'll find out that we don't need it. They put in the 200, put it in there, and they got 780, which is what we got, but they got plus a constant. But notice when they subtract 780 plus a constant minus 395 plus a constant, k minus k is 0, so that it cancels out. And I told you, it's just going to go away, so don't worry about it. Okay? And they're just showing it does go away because you're going to subtract the 2. So we don't even have to worry about it anymore. Just put that thing where the boundary is, and notice they came up with 385 just like we did working it by hand. Look good? Make sense? Okay, so I tried to simplify it as much as possible. Yeah, and they say, yeah, notice how it just canceled out. I said, okay, let's not make a big deal out of it, just not worry about it. And so they're just saying we can use any antiderivative. It could have been plus 4, it could have been plus 100. It doesn't matter what those costs, the fixed costs were, because they're going to cancel out. They're going to be the same for 100 caps as 200 caps, so it cancels out. Okay. Method 2. This is what we did as well. They can use the definite integral, and what they say they're going to do here, this total cost, area under the marginal cost curve. So graph the marginal cost, that's what we did. Graph the marginal, the derivative, get it the area under the curve from 1 to 200. That's the same thing. So they plug this in, they got the graph, they use some kind of technology, and they also got 385 as the area under the curve. Two ways to get that same answer. So integrate it, get the antiderivative, and manually sort of plug in the upper limit minus the lower limit. Do that by sort of analytical, or use the technology of graphing, find the area under the original derivative curve that was given to us. Less room for error. So we've got these two methods. If we use them both, we'll be very confident that we're getting the right answer. Or we'll be very confident that we made a mistake somewhere we got to find because the numbers don't match, right? And that's what happened to me yesterday when I was doing this, because I had an extra zero. I had 0.00, so that's when I simplified. That's why I don't like to simplify, because when I simplify, there's another error that could creep in, which did yesterday's lecture. Fortunately, I was going, wait, this is 242. It's not matching. What's the problem? Well, I figured it out because, they got to match. And so we go. Okay. So again, we could integrate it to the function, the big f of x, which is the antiderivative, plug in those values, and we'll get the same thing. This also was 385. Okay, it was what, 780 minus 395. We calculated those. So we've got two ways to do it. Now, I don't want you to curse my name later on, because when you get to the homework, some of it gets a little bit more complicated because there will be some U substitution in here as well. So that's why we had to do, was it 12.2 or 12.3? I think it was 12.2 was the U substitution, because it comes from the chain rule. So you'll get some more practice with that. Just look at it. So this one is really a good one because it's got everything pretty much that we've done up to date. So it's a good one to focus on for our test review, because it's got everything in here. If you can do this one, you're going to really build the confidence. And then again, on Thursday, it's going to be the same thing with to generalize it a little bit. Okay, so right now we're getting the area between the curve and the x-axis. Okay, that's a sort of a special case. We're going to look at the area under the curve and above another curve, not necessarily the x-axis. That's a more general case, and it's not that much different. Okay. Oh, I should have done this. We should hear music and angels coming from the heavens, because this is the fundamental theorem of calculus. It's so important. When you call something fundamental, that means it took people probably hundreds of years, maybe thousands, I don't know, but took them a long time to come up with this, and this is what all calculus really much becomes based on, because it connects the derivative, right, with the integral. It connects these two things that are happening: total value versus rate of change of that value. Those are the two things that calculus deals with, and this fundamental theorem connects those two with those two methods. If we've got the rate, we can find out the amount. If we've got the amounts, we can find out the rate. And again, in business, we need both of those. Sometimes we need what is our total profit. Sometimes we need what is the rate of our profit. Is it going up? Is it going down? How quickly is that happening? And sometimes it's okay to have, there's companies that operate with negative profit. Most retail operates with negative profit for sometimes what they call Black Friday, because that was when they started making money. When's Black Friday usually? they have it all the time now. It used to be Thanksgiving, right? Day after Thanksgiving was Black Friday, because that started. So it took them. They went 11 months in the red, losing money for 11 months, and because of Christmas, one holiday, spending the holiday season, I guess. All these companies suddenly make a profit. Interesting. So, and when you run a business, it's, again, it's okay not to be making a profit at per time if you know that the curve's going to come up and then in the end you're going to end up with it. So again, this is more formalized stuff. It's not so much what you're going to need, but we leave it in here for, I don't know why, but we just do. So generalizing, you have a lower limit and you have an upper limit. Now, it isn't required that the lower limit is smaller than the upper limit. It's just that that's a direction. And so in this class, we don't get into too much detail with that. And if you were in the engineering calculus, sometimes you actually, your upper limit is actually less than your lower limit because of the direction you're going. But for business, you really can't go back in time. So anyway, we'll find most of ours, the upper limit is larger than the lower limit, so it all makes sense, but it could also be switched. And it just talks about, the antiderivative has to exist, but the problems we're going to give you, they will. Okay, so if you're a math major, you have to say, well, maybe this one doesn't exist, and they will give you a few that don't, so you've got to figure that out. Business, we'll say, by the time you get the function, it's gone through some other department, and they're going to make sure it works, right? So now, let's just look at some examples. So we're going to emphasize what it is we're doing as students as we work through the homework. What are you going to be asked to do? Well, you're going to be asked to integrate. So again, with this setup, we've got our boundaries, but what we focus on first is the derivative function, which is 2x, and we want the antiderivative function. They gave it to us up here, but right, we'll just go through the steps. This is 2x to the first power. We add 1 to that, so we're going to get 2x squared, and then we divide by that new exponent, right? So that's integrating. We used to put plus a constant, but instead of that, because we have boundaries, it's going to cancel it out. I put a line here, and I said we're going to go from 0 to 1. And again, I could simplify this. This one is probably one I'm not going to make a mistake on. 2 divided by 2 is 1, so that does kind of simplify things. I'll go ahead and do that, but if it was more complicated, I might just leave it, because then just calculate it, right? So this is just x squared, like they say up here. Here's our function. So to calculate this, we plug in 1, the upper limit. So 1 squared minus 0 squared. And you'll see that you'll be happy when the lower limit is 0, because usually that's a very easy calculation. Plug it in and it's 0. 1 squared is 1, 0 squared is 0, so the answer is 1. Okay? That's method 1, or the first method. So fundamental theorem of calculus, integrate it. But we could also, and again, I encourage you, I'll do it, so since I encourage you to do it, I'll go ahead and show you. Just do it with the graphing calculator. Y equals, remember we put in the derivative function, which is just 2x. We do not integrate it. This is going to take care of it for us. We're going from 0 to 1. So in my window, instead of going from negative 10 to 250, how about if I just go from negative 1 to 2? So I've gone a little bit further than I need to. 2x, how big are we going to get? Well, probably not too big. Maybe I'll go to 5 as the big and negative 5. Just kind of, I could have left it at 10, but I just wanted to zoom in a little bit. Ah, there it is. There's our graph. We want second calc, number 7. And you could actually just hit the number 7 button. And now it wants the lower limit, which is 0, and the upper limit, which is 1. And it fills it in. We see we're getting area under the curve. The area under the curve is equal to 1. We got that both ways. Our answer is 1 both ways. 1 what? I don't know, because they didn't tell us what x was, so we don't really have the units on it, but it's an amount. It's not a rate. It's 1 stuff, 1 unit of stuff. 2 ways to do it, and that's what we'll do is we'll go through the homework. Not bad, huh? It's nice to have a way to just kind of plug it in, check it. Even with the ones that require U substitution, with those I might do this part first, get the right answer, so that when I do the U substitution, if I mess up on it, I'll know, fairly quickly. I say, okay, let me try this, let me try that. It's going to help you get down that U substitution, because there will be a question on the test that involves U substitution. And incidentally, on the test, if you forget a plus a constant, I'm not taking any points off, okay? So, because now we're not using plus a constant, right? So it's not as important. It's a small deal that we move beyond. All right, so what time is it? 8. We go to 8:45, right? I'm going to have to slow down because we're going to get done too fast. And no, we'll keep moving. Because we got a couple examples, and actually one of them's I think a little bit more. Anyway, we'll see. I did take one from the homework. So this one, again, we'll use both methods. We're integrating from 0 to 1. This function has 2 terms, and so when we integrate term by term. So when we integrate 1, which is a number, it is a constant, what do we get? We get 1x, right? And sometimes it's simple, but it's also hard because it's like, well, there's no exponent to add 1 to, but just remember that's x to the 0. 0 plus 1 is x to the 1. So it's just 1 becomes x. X squared, we add 1 to the exponent, so we're going to get, and we carry this negative, we're going to get x to the 3rd, and we need to divide by that new exponent. Okay, so that's just the rules for integrating, because when we take its derivative, we need to get back to what we started with. So again, if at this point, if you want to do that, at least mentally, what's the derivative of x? It's 1. What's the derivative of x to the 3rd divided by 3? The 3 comes down. Oh, the 3's are going to cancel. That's x squared. Okay, it all works. Do a sort of a mental check. We're not putting plus a constant. Instead, we're going to draw a line and say this thing's going from 0 to 1. The rest of this is algebra. We're going to plug in 1 for x, and then we're going to plug in 0 for x, and we're going to subtract the 2, and we're done. We got a numerical answer. So we plug in 1 minus 1 cubed over 3, and then we're going to subtract. I always sort of put a bracket or a parentheses on the second part just to make sure we're subtracting that whole thing. I put in 0 for x minus 0 cubed over 3. And notice when you plug in 0, a lot of times we're going to end up with 0. So subtracting 0, it just sort of disappears. It makes that part of the calculation easier. And they're giving us some, using 1. So 1 is just 1. 1 cubed is 1, so then it's 1 minus 1/3. Get a common denominator, so 1 is actually 3/3, right? 3/3 minus 1/3. So our final answer should be 2/3. You might, when you're going to use a calculator, is it going to tell you 2/3? Probably not. It's probably going to give you a decimal. So take 2 divided by 3, turn it into a decimal, and you'll see you'll get 0.066666 repeating forever, and then finally a 7 at the end. So when we do the technology part, we're not going to see 2/3. We're going to see 0.66666. Incidentally, I forgot to mention this to the other class, but someone came up at the end and said it's not accepting my answer, and I put it in there. I said, oh, you put a decimal. It probably wants the fraction. So on the homework, you can't put in 0.6667. It'll mark it wrong. You have to put in 2/3. So while you can still use the calculator to check things, they're also wanting to make sure you're doing it by hand. So that, and the way they're doing is they will only give you credit if you put in the fraction. Again, you can get around it because, no 0.3333 is 1/3, 0.666 is 2/3. So know a few of those and back change, but at least on its first attempt, they weren't. There may be a place, if it says round to 2 decimal places, then you're safe putting a decimal. Otherwise, what they want is a fraction. So now, again, we're sort of done, but what we're going to do is we're going to use the other method of the calculator. We go to y equals, clear that one out. We put in the function, the original function, 1 minus x squared, right? That's what we had, yeah. Just like was in the problem. We'll check our window. We're going from -1 to 2. Our boundaries were 0 to 1, so that works. I think these will work too. If not, we'll move them up higher. Yeah, we can see the graph, and we know we're going from 0 to 1. So we do second calc. And then incidentally, do practice these. Do them a few times. Lower limit is 0. Upper limit is 1. It's shaded it in, and we got the 0.6666667, which is 2/3. Matches. We're good. Okay, so we do it. And again, when you work these, you could do it either way, whichever one you want to do first. But it's just remember, tell yourself, even maybe talk to yourself. When I'm doing math, I'm always talking to myself. Some people think well, who are you talking to? I'm talking to myself, right? But talk it through. Okay, this is the derivative graph. This is the area under the derivative graph that gives us the same value if we got the antiderivative graph and we plug in 1 and then subtract off 0. So that's what's going on. Okay. Come back here. And now, again, I'll let this kind of walk us through. This is how they did it. They integrated just like we did. They still put plus the constant, but I said I'm way past that. Let's just, we know it's going to cancel out. We're going to do this, and maybe in the 40 years since I learned calculus, they've changed it. But I was taught to sort of put the limits as a line, and then put the kind of mimic the 0 to 1. But whatever you want to do, that works. Okay, plug it in, get our answer 2/3. Okay. They didn't show the graphing method, but that's a second method. And again, I encourage you to do it with each of them. So let's look at an application. What we're going to do is this is the same problem we worked when we were it's going to calculate the area between the graph and the x-axis. So this is one we did with the oil spill, the oil leak. We have the rate, right? So this is exactly the same problem, but we're just now going to use the new techniques. We're given a function. We're told oil is leaking. And we know this is a derivative because we've got this word per barrels per day. That's a rate. We know this is a derivative. It's going from 0 to 20. T is days since the failure. Compute the total. So those are the words we're looking for. We're given a rate. We want the total. We're going to need to get the antiderivative or the area under the curve or both. The total volume of oil released during the first 20 days. So that means from day 0 to day 20. That's our limits. That's what they're giving us. To solve this, we're going to integrate from 0 to 20, because that's what they're asking. They're telling us the boundaries. We put the function in that they give us. dt. And if you want to change it to x, you could. I usually like x better than t. So that's actually, so it's not too bad to set up the problem. They've given us a derivative. We just do it. Now we just need to integrate. We'll also do this with the technology, and we'll see it. That's this. I think we did this one with Riemann sums. We'll see that we get, and we ended up somewhere around 600 as we got it more and more accurate. We'll see what we get now. So we integrate t squared. Again, add 1 to the exponent. So this is going to become 0.08 t to the third divided by 3. I'll do it that way. I'm just going to leave it like that. I don't want to simplify because I'll probably make an error, and makes it worse. So I'm just going to leave it because it's all going to get plugged into my calculator in the end anyway, right? 4t to the first, again, add 1 to that, so we're going to get, oops, not 2, add 1 and get 2. So we get minus 4t squared divided by 2. Now that one I might simplify, but you could, 2 goes into 4, that one's not too bad. 2 goes into 4, there's a 2. But again, I could make an error if I'm not too careful, so maybe I leave it. And then finally, we integrate the last part. 60 is just a number. Just remember, it's going to be 60 times the variable, 60t. No plus a constant. Instead, what I do is I come to the end and I say we're going to go from 0 to 20. Again, that's my notation. I don't know if this book uses it, but it's how I was taught, so we'll use it. Looking there, since each term has a variable, when I plug in 0 for that variable, the whole thing goes away at 0, right? It all becomes 0, so that's always nice. Really, we just need to plug in 20. And it's all arithmetic from here. I'll leave it as 20 squared plus 60 times 20. I will put the minus 0 just to emphasize that, yeah, we did plug in 0, but I can see it's, I don't want to rewrite all the things out and just have 0 anyway, but you plug in 0 for each of the t's, everything's going to be 0. 0 minus 0 plus 0, still 0. So that's the lower limit. That's taken care of. And so now I just plug that in my calculator, and I could do it all in one line or something, but again, just make sure you've got it entered in correctly. For some reason, when I was doing this, I put an extra parenthesis, so I got a weird answer. I said, okay, that's why we check it. Because, just because I put it in my calculator doesn't mean it's right. My calculator probably was right with what I told it, but oftentimes I'm entering in stuff. So 0.08 times 20 raised to the third divided by 3 minus 2 times 20 raised to the second power plus 60 times 20. And if somebody could, at least one or two of you, if we get the same answer, I'm going to feel better. If we don't, I'll know I messed up somewhere. 613.333. Okay, good. And then we get 613.333. And I think this is one that was on there, and we had to convert it to thirds or something. It was something like this. So again, this answer might not be acceptable by WebAssign because they want it as a fraction. Well, I don't know. I'll figure it out, right? So this also could be written, so let's do that here. It'd be 613 and 1/3 as a mixed number. You remember how to take a mixed number to turn it into an improper fraction? Maybe it's, yeah, we did that in 4th grade, but I don't remember anymore because we stopped doing that. You take the 3 times this, and then you would add the 1. So 3 times 613 is 1,839 plus 1. So this will be 1,840 thirds. That would be the answer that WebAssign would be looking for. Okay, so just be able to convert them over. The test, this is a perfectly, in fact, actually it's a better, I think, answer. Okay, we could do the same thing with the calculator. Again, get the windows right and everything, graph it, and we'd see that. I think we probably did this when we were doing the Riemann sums, but we'd see it's also the area under the curve is also 613.33. Okay, so far we good with that? I think I've got one more example, which I took directly from the homework, mostly just to get over the vocabulary that they're using, because otherwise you'll read this and say, what are they talking about? They're just saying to do basically what we're doing here. Okay, and yeah, they walk through it in their solution. They set it up, going from 0 to 20, just like we did. They integrate it, just like we did. Oh, they do sort of use this with brackets, 0 to 20, right? They plug in the 20, they plug in the 0. So again, a little bit more. We'll see over here we do get 0. Over here they did each one, and yes, they did 640 over 30. So, but they still did 613.333. But again, in WebAssign, they probably wouldn't get their own homework right, because unless they say decimals, this is what they want it as a improper fraction. They don't say it, but that's what they want. So here's our last one. We'll do together, and what I wanted to say, so they calculate the total area of the region described. And remember, region described is area underneath the derivative curve. Now they don't get, so do not count area beneath the x-axis as negative. I'm going to show you what that means, bounded by the curve. So this is our function. This is our derivative. If they don't call it a derivative, but it's the area of the curve and the x-axis. Okay. And the lines x equals 0 and x equals 25. Well, these are vertical lines. So it's just, here's x equals 0, here's x equals 25. If you remember what the square root function, it'll look something like this. And what we're going to do is get the area under the curve, which would be the same thing we would get as if we integrated from 0 to 25, the square root of x dx. Okay, so we can do this two ways. Again, we've got two methods in the homework if you want to just do it, but basically we could graph it and we can get this. So let's do that first, so we've got a good answer to work from, and then we'll do it with the sort of by hand, the analytical method. So let's clear this out. Oops, clear it. So we want square root of x is our function. It's our derivative, right? We're going from 0 to 25, so let's check our window. This is going from -1. Let's go to 30, just so we can see everything that's going on. Square root, our function's the square root. We're at 25. Square root of 25 is 5, so we don't need to go. 5 is probably enough. Let me go to 6. And then let's just hit the graph, and yeah, we see everything. Let's use our technology. Second calc, number 7. Arrow up, I got number 7. The lower limit is 0. The upper limit's 25. And I see the picture. It's the area under the curve and the x-axis. That's what it's going to give me. That's what the built-in function is. And it's 83.3333. Okay. Now, they might not accept that answer, but we've got this as a check. So let me go ahead and come back here. So we got, over here, we'll put 83.333, which is, we have to recognize that's 83 1/3. So we take 3 times 83 and then add 1, and that will give us the improper fraction 83 times 3 equals 249 plus 1 is 250. Because this, I think the homework, I think he had even gave him, he says, you worked it. He says, but it says it's wrong. And I said, okay, let's see. I bet you they want this fraction. And we put that fraction in, and he got it right, which is basically what he had. So now we're going to work it the other way, which is, again, what they're really wanting us to sort of do. Remember, square root of x is, how would we integrate that? Maybe by first writing it as x to the 1/2 power, because that's just it's a change. Its square root is to the 1/2 power, but we can work with the 1/2 power. We really can't do much with the radical. I mean, we don't, So what do? So I'll put the dx. We add 1 to the exponent, and when we've got fractions, let's do it as 2/2. So when we integrate this, we get x to the 3/2. 1 plus 2 is 3. Denominator stay the same. and then we divide by that new exponent. Remember, when you're dividing by a fraction, you're just going to flip it and multiply. So what ends up happening, well, let me put my boundaries here, 0 to 25, because it'll be helpful to, you can do this, but you'll, again, in the calculator, you might, it's easy to mess up. So I'm going to invert this. This becomes, the 2 will go into the numerator, right, because 3 over 2 becomes 2 over 3. So this becomes 2x to the 3 halves divided by 3. It might be easier to see that way. Okay. Again, going from 0 to 25. And we can see if we plug in 0, we're going to get 0. So this is going to be 2 times 25 to the 3 halves power divided by 3. So in a sense, this will be easier because we can do this calculation and we just leave it over 3 and we'll get it right, rather than having to convert a decimal over. Then minus, I'll write it all out, 0, 2 to the 3 halves over 3, and this whole part here is just 0, right? So this is 0. So we just have to calculate this. 3 halves, so this is, if you take 25, you take the square root part first. Square root of 25 is 5. And then you cube it, because there's still to the 3rd power. 5 to the 3rd is 125. And then 125 times 2 is 250. Divided by 3. Again, you could turn it into a decimal, but WebAssign would probably want you to leave it in this form to get it corrected, because it wants a improper fraction. Although it won't say, it didn't say in the instructions about decimal place or anything. I just had to figure that's probably what they wanted. Okay. And again, you could plug this in your calculator. You don't have to, how did you do this? Well, just put 2 times 25 raised to the 3 halves power. It'll give you 250. Leave that, and then don't divide it by 3. I mean, write it, but put it in as a fraction. Okay. There are a few. There's a I don't know, 5 or 6 of them that are fairly simple in this form, where the integration's not too taxing. But there are some that are going to require you to use either U substitution or the shortcut rules. So sometimes the shortcut rules, you could look, if you've gotten good at them. 40 years later, I'm still not good at the shortcut rules, so I just do the U substitution. It makes more sense. But do that. There's maybe 3 of those, 2, 3, maybe 4. I didn't count them, but there's a few of them that will need, that the derivative comes from a chain rule. Okay, so it's a reverse chain rule thing. That's where we use the U substitution. It'll give you good practice. But again, the technology, you just put that function in there, graph it, get the area under the curve and the x-axis, and you're good. Okay, so that's it. I used up enough of class time that probably was worth your while. Work on these, and then Thursday we're going to be looking at getting the area between 2 curves. So instead of just the x-axis, the second curve, the bottom becomes a curve itself, and we'll see it's not too much different. Not too much different.